go ahead and start. Sorry. So let me go ahead and start once again. Welcome everybody to the online SPICE and SPIN+X seminar series organized by the Spin Phenomena Interdisciplinary Center that I lead together with Karen Eversosite and the Collaborative Research Center SPIN+X between Casas Latin and Mainz, which is led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe. As usual, this is a Zoom webinar system that you have to ask the questions in the Q&A during the talk, and I will give you the opportunity to speak and ask the question directly to the speaker after the talk. Please be polite, of course, and then you can actually answer and comment among yourselves. We start every Wednesday at 3 p.m. most of the Wednesdays. So far, we've been pretty regular. Maybe in the fall, we sparse a little bit. And next week, we have Rembert Dwight and Hideo Nafrilas, and we'll try to find a speaker for in between. But today is a pleasure to invite a young upcoming talent, Saima Siddiqui. So I'm so sorry to butcher your last name.
No reason.
So he's a very active postdoctoral associate in the University of Illinois in Champaign. And she already did some great work in her PhD thesis, PhD time in MIT. And she is quite interested in novel physical phenomena and electronic spin systems, of course, as there, but wants to focus a lot now on emergent artificial intelligence and how to use spintronics to exploit that. And this is a theme that we've heard a few talks about. And this one is, whereas we heard already from Mark Stiles, the theoretical front of it. Now this is the reality of how you can actually maybe do it in experiments. So I'm going to stop here, and then I'm going to ask you to share your talk, and I'll mute myself once you start. And please go ahead, Saima, and we're looking forward to hearing you talk. So go ahead.
Let me share my
the presentation.
Yeah.
Okay, perfect. Go ahead.
Okay. Thank you, Professor Zinova, for the nice introduction and for inviting me to the online SPIN+X seminar series. And I really appreciate the opportunity to present my research on such a big platform. Today, I'm going to talk about artificial neural network and how the Spintronic devices can form the basic building blocks for this kind of neural network. So let me talk about first what motivates the scientists and engineers all over the world to explore the neural network at the first place. So here I'm showing the architecture of modern computers, which is called von Neumann architecture, and where the memory and the processing unit are separated from each other. And whenever the data need to be processed, it has to be bring back and forth between the memory and the processor through this cache, through the interconnects. Now, cache here is also another kind of memory with a very fast response time. And so it takes a lot of energy and also processing time to bring this data back and forth to do the shuttling between the memory and the processor. But this problem was always there ever since the modern computer was invented. But this was not a bottleneck as long as we are not doing some very data-intensive computation. But today, we are in the cognitive era, and we are not just happy doing the very precise computation or very precise image processing of our data. Rather, we want our computers to make the decisions or sort any images based on those image processing. So for the traditional image processing, it requires to do element-wise multiplication. So the image is represented by a matrix. It is a two-dimensional matrix. And for the processing, it's multiplied with the filter, which is also a two-dimensional matrix. And for multiplication, this both filter and image need to be bring back from the memory to the processing unit. And after doing the multiplication and summation and other operations, the output image is also stored in the memory. So it takes a lot of energy and resistive losses are happening between the interconnects. Now, this is the traditional image processing, and for doing the classification task, the amount of processing is even larger. So now the matrices, the input and the filter, are not only two-dimensional matrices, rather they're three-dimensional matrices, and the output is also a three-dimensional matrices. So you can imagine the resistive losses in moving the data around. And here, when I'm showing this operation, it's an operation within a single layer. And to get an accuracy of human level for the classification task, we need hundreds of these layers. So we need to find the solution of the data shuttling problem now. And naively, one way would be bringing the memory close to the processor, so less interconnect loss and less wastage of time. Or processing inside a memory would be another option, so that we can completely eliminate the interconnect loss. The system that performs this kind of layer-by-layer operation are usually called neural network because of its similarity with the neural system in human brain. Now, in human brain, data storage and the processing units are co-located, and it performs the data classification task most efficiently. So computation inside a memory would be a more elegant solution rather than bringing the memory close to the processing unit. And I like to mention here, as Professor Sinha said, that there are other talks in this seminar series on the neural network. But in this talk, I will focus on the artificial neural network. And the other type of neural network, for example, is spiking neural network. And in a couple of weeks ago, Dr. Mark Stiles has comprehensively explained that how the spiking neural network work. And if you're interested to know about those kind of SNN, I recommend to listen to his talk, which is available in the SPICE YouTube channel. I also recommend on listening Dr. Julie Grolier talk, where she have shown the nano oscillator as the building block for neural networks, which is a very promising approach for realizing this kind of neural network. And since we are talking about neural network, we must look into the brain. And a brain is usually composed of billions of unit cells, which are called neurons. A single neuron is connected with thousands of other neurons with the connections called synapses. Now, these synapses store the weights, and just like the weights inside a filter, or so whenever the data comes in from other neurons, that signal is multiplied with the weight stored in the synapse, and then the, say, neuron or cell body sum all the signals coming from different synapses. And it decides to send the signal to the next neurons based on a thresholding operation. So if the signal is above a certain threshold, it sends the signal to the other neurons. If it's not, then it does nothing. So if you want to look into what are the main operations this whole system does, it can be divided into two main operations. One is the linear multiplication and accumulation, and the other is nonlinear operation to converge any problem, so that whenever it does the summation of all the weighted inputs, the signal doesn't blow up, rather it always finds a converging solution. So now, as an electrical engineer, we want to create the circuits for this neural network, and we want to compute inside a memory. So one way of doing the multiplication would be simply relying on the Ohm's law. So if our input is a voltage, and output will be the current, and this will be the multiplication of the voltage times the conductance. Now the device that will represent the conductance is the synaptic devices, and it will store the weights, just like a filter or just like the synapse in the human brain. Now to sum all the multiplication of the current, we can rely on the Kirchhoff's law. So the current sum of the end of this column would be the voltage times current coming from different, voltage times conductance coming from different branches. And at the end, we can use another storage element so that can store the thresholding function, and we call it as an activation function generator. And this multiplication, as I showed before, is the multiplication of matrices. So we don't have to rely on one single column. Rather, it can be multiple of columns, so that we can do the complete multiplication of a matrix just with a single multiplication task or with a single clock. So about here, the synaptic devices, accumulation of all these synaptic devices are behaving like a synapse in a human brain. And at the end, when the thresholding function is, or activation function operation is done, it's behaving like a neuronal activation, if you think about the similarity with the human brain. So the idea of creating this synaptic and activation function generation is computation inside a memory. And one of the good way to use the memories is using the non-volatile memory. So once you store this data, if you power down, you don't have to worry about losing the data. And using this circuit or devices later after powering off, you can use that after other operations when you power on, and the signal will not be lost. Now, looking into the non-volatile memories, there are many non-volatile memories, and here I'm showing, mentioning three prominent options, and these are all non-magnetic, non-volatile memories. So one is phase change memory, and the other is resistive random access memory, and the other option is the conductive bridge random access memory. Now, I'll briefly introduce what these memories are to give you understanding of how they operate. So the phase change memory, there is a chalcogenide glass between two electrodes. This is the top electrode and this is the bottom electrode. And whenever the current applied between these electrodes, that heats the chalcogenide atom, and also it can cool the chalcogenide. So depending on this heating and cooling, the chalcogenide glass has a different phase. One is the crystalline phase and the other is amorphous phase. And depending on those phases, the resistance between two electrodes changes. And this is how the non-volatile memory store its different states. Now, so phase change memories have been extensively studied over the past years, and they also have been produced, mass-produced by the semiconductor industries. The next option is the resistive random access memory, and in this case, a metal oxide is sandwiched between the top electrode and the bottom electrode. And when an electric field is applied between these two electrodes, it creates and moves the oxygen vacancies, and that create a filament of these oxygen vacancies inside this metal oxide. And that changes the device resistance. And this is the way of changing the resistance state or the memory of this random access memory. And one of the good advantage of this resistive random access memory is the metal oxide are usually the oxide the semiconductor industry already use their fabrication facility. So it's really easy to fabricate in the industry. The problem is, though, the stability of this oxygen vacancy is not very good. So this device is not very reliable, and there is a reproducibility of this electrical characteristics from device to device and also within a single device. Now, moving on to the third option is the conductive bridge random access memory. And this is something similar to the random access memory. But here, this metal oxide is replaced by the solid electrolyte. So what happens, and one of this metal, the top electrode in this case, can create mobile metal ions, which can travel through this solid electrolyte. And that happens when you apply an electric field between these two terminals. By application of this electric field, this metal filament form and bridge with the bottom electrode. So the resistance will be low. And with the application of opposite electric field, the metal atom goes again to the top electrode, so the resistance will become high. Again, this conductive bridge random access memory great, but there are some limitations because this creation of this filament is kind of a stochastic process. So these are not very reproducible. So behaving as a memory, there are a lot of research going on how to create these in the industry. All these are great options, but they have limitations. And as a magnetic community, we definitely know about our magnetic random access memory, which is STD-MRAM, and which is based on magnetic tunnel junction. And I don't have to go through the detail about the magnetic tunnel junction, since we know that this is the low resistance state when the two ferromagnet of this stack are parallel, then the resistance is low. And when they're anti-parallel to each other, there is a high resistance state. These are great in terms of stability, in reproducibility, but one of the limitations is the tunnel magnetoresistance, which is the ratio between the resistance state with the low resistance, which is not very great. And this is the main limitation of magnetic tunnel junction compared to other non-volatile memories. But other than that, it's a very, very good options for as a non-volatile memory. I like to talk about the reason being because I wanted to show all the different kind of non-volatile memories that to show you how this Spintronic devices fit within the memory within the industrial options. What are the options? How they fit and how well they can perform compared to other non-volatile memory. And so here I'm showing one of the comparison of write energy compared to the write time. And we want our memories to be energy efficient. And also we want to operate this memory fast. So if you look into all the different options of this non-volatile memory, here the STD-MRAM is represented by this green diamond. And they actually have the lowest writing energy and they can operate with the shortest write time. So they have the favorable write energy, write time compared to the other non-volatile memory. And not only that, if you look into the size of these memories, like so that you can estimate how much area you need or how dense your memories will be, then also again, we want smaller size of this each memory bit. And it's not the best, the spin transfer torque MRAM memory represented by this green diamonds, but it's better than most of the other options in terms of cell area. But most importantly, these materials we use for this fabricating magnetic tunnel junction or STD-MRAM are compatible with the semiconductor technology or complementary metal oxide semiconductor technology. And that gives a huge benefit of using these kind of devices as a non-volatile memory. The reason I go about all this talk about non-volatile memory is that that we are going to use these Spintronic devices for particularly this operation where we want to create these neural networks. Now, neural networks, as I discussed before, require the non-volatile memory for storage, creating the synaptic and the thresholding devices. So this is the outline of my talk today, and I will talk about how we can use the magnetic tunnel junctions for creating analog synaptic and thresholding device. And when I'm talking about analog, that means the output conductances or resistances of these devices will vary as a continuous fashion. In the second part of my talk, I will show you the digitized version of these synaptic and thresholding devices so that now this conductance or resistances will change as a stepwise fashion. And at the end, I will show you a system design by using the analog devices I will show in the first class. Now, before going to the analog device, let me take a brief detour and show you a 3-terminal magnetic tunnel junction device. And what we are trying to do when talking about neural network or synaptic devices or thresholding devices, we want to compute inside the memory. So that's why I brought this up here. This 3-terminal device not only work as a memory, but rather it can also do some computation. But it does computation in a in a digital version. So it's all about 0 and 1, not an analog or digitized version of the continuous resistance chains. Rather, it's always bitwise operation. So what we had that time, that we had a domain wall in the free layer of this tunnel junction, 3-terminal tunnel junction. And when the domain wall is on the left side of this tunnel junction is in the parallel state. So the output current is high, so the output resistance is low, and that represents bit 1. If you apply current to move the domain wall, then because of the spin transfer torque, the domain wall will move, and it will go to the other side of the tunnel junction. Now the magnetic tunnel junction is the anti-parallel orientation, so it has high output resistance or low output current, so that represents bit 0. And we fabricate this device. And in this case, the free layer where the domain wall exists is designed as a semicircular arc so that we can create the domain wall easily with magnetic field. And the magnetic tunnel junction is under this wire, and these 2 terminals are represented by these 2 terminals in the SEM figure. And we started with the domain wall on the left, and then we apply a small bias field. And this field is not high enough to move the domain wall by itself, but it helps to remove the threshold current, move the domain wall. So when we apply it input voltage to which converted as a current, and that after a certain threshold, the resistance changes because of the domain wall moves on the other side of this tunnel junction. And we can measure them electrically. And so you see that when the voltage is about a 3.8 volt with a voltage pulse of 1 microsecond, then there is a sharp change in the resistance. And this device, you can think that, yeah, it shows 1 and 0. It can be seen as a memory, but it also operates as an inverter. So when the input voltage is low, the output resistance is low. And when the input voltage is high, the output voltage is high, which is the behavior of an inverter. And this device not only operates as an inverter, but it can also be operated as a NAND or NOR gate if we have multiple inputs instead of 1 input current, and if we adjust the width accordingly. So now the question is, why talking about this device, how they're related with the system, what I wanted to create, this 3.3, this cross-point architecture. So the idea is we want to replace the synaptic devices with the device I have already shown. Then the question is, what are the criteria we need to fulfill to replace the synaptic devices or these conductors with the domain wall-based magnetic tunnel junction? So these are the criteria. These are the important criteria we need to fulfill. The first one is non-volatility, which I already told you that's magnetic devices non-volatile. You already know that. Then the next criteria is we need to generate multiple resistance states. So this is something we haven't done yet, because now all I have shown you that 0 and 1. Then the other criteria, this is another important criteria, is that the input and output relationship of this device have to be linear. And this criteria is identified by the circuit people who define that if you have a linear input-output relationship of the synaptic devices, the design of the circuit becomes very simple. So it doesn't require very much overhead to define the weights every time, and that we can take that full advantage of using this kind of computational within the memory. So here we are proposing to how to modify our previous device to get a synaptic device. So now the domain wall is not in the one side or the other side of the reference layer. Rather, the domain wall is under the reference layer. So based on the position of the domain wall, now the output resistance of this tunnel junction will be a linear combination of the parallel and anti-parallel resistance. Here, the red region shows the parallel orientation of the free layer, and this blue region shows the anti-parallel orientation of the free layer compared to the reference layer. And from our analysis of the domain walls, magnetic domain walls, we know that the domain wall, whether we rely on spin transfer torque or a spin orbit torque, they move linearly above a certain threshold of current density. So And with this magnetic tunnel junction, by utilizing this equation, we can transfer this linear motion of magnetic domain walls into a linear change in the resistance. So that seems very, very simple. And we are not the only group thought about this simple solution. There are other groups pioneering working on this, especially have done a lot of circuit and simulation and architecture analysis. It's Professor Kaushik Roy from University of Purdue. So it's great that we can create this linear behavior of the synaptic devices and replace them with the domain wall with magnetic tunnel junction. Then the question, what about this activation function generator? Is it possible to change them also with this kind of device? Again, we want to look into the device. We want to know what are the criteria we need to fulfill. So in this case, the first two criteria, the non-volatility and multiple resistance state, we know with the device, we already can generate that. But one of the important difference between the synaptic device and the activation device is that in the activation device, the input-output characteristics have to be nonlinear, because that's what we are trying to do. We are doing the thresholding. And in this nonlinearity, there are some preferable nonlinearity for doing the threshold. So here, to create this active nonlinear activation function, we use the similar device. This is similar in a sense that it is three-terminal. It has a domain wall in the free layer. It has a long reference layer, and we are relying on the domain wall motion in the free layer to change the resistance state. The important difference in this case is now the layer under this free layer, where we apply the current, and is not, the width of that layer is not constant. The width changes continuously along its length. And in this particular device, we are relying on the spin orbit torque, not the spin transfer torque, to move the domain wall. So to show you how this thing operates is here again, the input is the current, and the output resistance is again the function of the combination of parallel and anti-parallel resistance based on the domain wall position. And this is the same equation we are using, where the domain wall velocity is a linear function of the current density above a certain threshold. But now we can elaborate this current density into the width and the depth and the thickness of this layer of this spin orbit torque generating layer. And by making this equation more explicit, we can come up what kind of width function we need. If we have a certain type of input-output relationship, we get this differential equation. So if we know the input-output relationship we want to generate, we can figure out what kind of width we have to create for generating this kind of nonlinear thresholding. So to give an example, sigmoid is one of the popular functions used by the machine learning community or neural network community, people especially who works in the software version of the neural network. So they use this kind of sigmoid function, where this is the input-output relationship. So in the x-axis, it shows the input, and the y-axis the output, and it has this kind of hyperbolic tangent-like behavior. And we can predict that from our analytical model, what we can generate this, what kind of width we need. And we take that width function and put it in our micromagnetic simulation. Sorry, there is some delay. Sorry about that. Okay. Put it into our micromagnetic simulation, and we see that the micromagnetic simulation give us the exact solution that where the domain wall position would be based on the current density of the input current density. And here the resistance is converted, assuming a certain type of parallel and anti-parallel resistance. And this is just the simulation version of that. We have done also an experiment. Again, it's taking some time to going to the next figure. Sorry about that.
No problem. That's the difference between theory and experiment. The theory is
Good timing then.
There you go.
Oh, I don't know what happened.
Yeah. Did it freeze or?
Yeah, it's showing like it's not working.
Okay. Are you able to continue forward or not?
No, let me stop share for a moment.
No problem. Yeah. It can happen with some animation sometimes. Just in the meantime, just as we restart, reminded that everybody whoever has some questions to please write them on the Q&A, and I'll, for me to be able to pass the microphone later on. Okay. Is it back on?
Yeah, let me share again.
Okay. Okay, perfect.
Sorry about that. So yeah, here I'm showing the results of an experiment. So this is the image from a magneto-optic car microscope. So you can see the wire. It is the ferromagnetic layer on the top has a constant width, and the green region shows, say, upspin, and the brown region shows the downspin. And you can see on the bottom, there is a wire, which in this particular case is platinum, is shaped as what we got from our analytical calculation. And we applied current with, and you can see the domain wall here. So we applied a current between these two terminals to move the domain wall, and we see that we indeed can generate this kind of sigmoid function from our device that we designed from our analytical model. So experimentally, which is great. So to just summarize what I have shown you so far is that we can generate this kind of synaptic functionality with linear input-output behavior, and also nonlinear input-output behavior for the thresholding function using similar kind of domain wall-based magnetic tunnel junction device. Moving on, I will show you a variation of the device I have showed, so which is the digitized version. Now, the input resistance will not change will change linearly, but it will not be a continuous fashion, rather in a stepwise way. And for that, we have designed our magnetic tunnel junction because we wanted to read these things electrically. And this is a cobalt iron MgO based magnetic tunnel junction. We have a free layer on the bottom, and we have a reference layer on the top. And to make the reference layer hard enough so that it doesn't switch easily, we have a synthetic antiferromagnet, which is based on the cobalt platinum layer. And this is the measurement for a continuous magnetic tunnel junction layers. And you can see that the free layer switches very easily with magnetic field, where the synthetic antiferromagnetic layer switches at higher field. And we can generate all these different sorry, it's happening again.
That's a good time to ask Axel to buy your new computer. And since he's watching.
So what I wanted to talk about that, since you can see that 4 different resistance state, 4 different magnetization states, so that defines that that we can see all the different magnetization state of coming from the synthetic antiferromagnetic layer and the free layer. So I'll move on to the next slide so that I move easily, or go to the next slide easily.
Okay. Yeah, we're online.
So after creating these thin films, we also characterize the magnetic tunnel junction after fabricating the tunnel junction of this is the fairly large size of tunnel junction. And we see that the TMR of, we can see the fairly distinctive parallel and anti-parallel resistances. And the TMR of this, oh God. The TMR of this layer is about 44%. So now in my first device, when I was showing an in-plane magnetic tunnel junction and showed you a semicircular arc to create the domain wall easily, the difference between this magnetic tunnel junction and this is a perpendicular magnetic tunnel junction. So the question is how we generate this magnetic domain wall in this kind of devices. So for that, we analyze our devices more. We look into the free layer where there is no reference layer, and we see that that part switches with a very small field, about roughly 20 to 50 worsted. But if we have a reference layer on the top, if you have a reference layer on the top, that part switches with a high magnetic field, even a lot higher than what the free layer should switch. So this is there is some reference layer dependent switching of the free layer. So now, if we start with a continuous layer, where all the domains are parallel, and I'm very sorry about this.
No, it's okay. That's why it's a live talk, so right. Can also happen during a normal talk. Axel wants to talk. All right. Do you want to restart the computer maybe?
Let me try one more time. If this doesn't work, then
And restart the computer. It's just part of the computer all the time, so it's no problem. But Axel has agreed that he will buy you a new computer. Yeah.
Okay, sorry. Okay, so what I wanted to say is now if we have, if you started with a continuous layer, which is everything is aligned, and then the reference layer is also aligned with the free layer. Now, if we apply the small bias field, the regions in this side will switch, but the region under the reference layer will not switch, because if we apply, say, bias of minus 200 worsted, just slightly above anything above 50 worsted, that will switch the free layer where there is no reference layer, but not the region where there is reference layer on the top. So there is domain wall around the edges of this tunnel junction. So now we have a domain wall. We want to move them, and this is the test setup we used. We connected the two layer, and we apply pulses by using a pulse generator. And after applying each pulses, we measure the resistances in between these pulses, and the amplitude of the pulses increases as we keep applying the pulses to figure out what's the threshold to move to this domain wall. So to create a synaptic wave generation, we now design a device where we have multiple of this tunnel junction, And the bottom wire now is not the same width along the length. Rather, the width of this wire varies linearly along the length. Are you guys seeing my mouse? No.
No, I'm not.
Okay, how about now?
Well, now I see. No, I see the mouse. Yes, I see.
Okay, cool. So the wire width varies linearly, and we have in this particular prototype device, we have designed 9 magnetic tunnel junctions at the top, and they are separated equal distance from each other. So when we keep applying the increasing field with the small voltage or small current, we see the first switching. So that means the first domain wall under this magnetic tunnel junction moves, and that changes the resistance of those first tunnel junction. And if we keep increasing the amplitude, the current amplitude apply between these two terminals, between these two terminals, then the domain wall moves for the domain wall under the second magnetic tunnel junction moves, and then we measure the second step in our measurement, and so on. We keep increasing the current, and that moves all the domain walls onto the magnetic tunnel junction, and we can see all the different steps coming from the different tunnel junction. Now, one significant thing we observe that here we have 9 magnetic tunnel junction in these devices. So we are supposed to see 9 steps and 10 different resistance state. But on this particular case, we only observe 8 steps or 7, 8 different resistance states or 7 steps. So the thing is, the last 2 magnetic tunnel junction does not switch, because the current to move this domain wall under this tunnel junction or under this reference layer is high enough that can damage the device. But the good thing is we have these resistance changes, which is very linear with the input current, so that if we utilize this device as a synaptic device in the circuit, then the extra overhead that requires for cases where this linear resistance change is not available, we don't need that extra circuitry to that will save much of the circuit space, and also that saves a lot of energy, which is required for operating those extra circuitry. So we can use this kind of behavior, this kind of devices with magnetic tunnel junction, multiple magnetic tunnel junction, to create the synaptic devices, and this is the digitized version of that. Now, moving on to the next one, the synaptic device is, again, for an example, we have chosen the sigmoid activation function, which is very popular for the software community. And in this case, we also have the similar device. And we have multiple tunnel junctions. And from the similar analysis, I can tell you that we have domain walls on the edges of this reference layer. In the free layer, we have the domain walls. And the important difference between the synaptic function and activation function in this case is that now the tunnel junctions are of not same size, rather they are of different size. And this size was designed in a way so that we can create this activation function, the sigmoid type activation function. So this is an analytical results that what kind of design we want. We want this analytical sigmoid function, and I'm here showing an operation of just a mirror version of what we have here. And these are the resistance steps should come from the magnetic tunnel junction. So the small magnetic tunnel junction should give a small resistance step, where the big tunnel junction will give us this big step to create this non-linearity of those functions. So for measurement, we use the same measurement setup, where we apply pulses, measure the resistances after each pulses, and the pulse amplitude is increasing from one pulse to the next. And this is the measurement of about 75 devices, where we shown that if we have this device and they can create this kind of sigmoid functionality, which we wanted to generate from and calculated that from our analytical design. And again, I'm here showing in the not exactly the shift, the sigmoid, rather it's more like a mirrored sigmoid, just the mirror version, if you assume along the current axis. So to summarize the second part of my talk, that I have shown you that we can generate this kind of synaptic devices and also the thresholding function devices and read them also electrically at the same time. So it's possible to create the circuitry out of these devices. So let me talk a little bit about the energy required to operate these devices, because that was the main motivation, that how much energy we can save by doing operation or doing calculation inside this kind of non-volatile memory. So for the prototype devices, the power required to switch is about 150 microwatt to 2 milliwatt. But the current pulses we use is only 8 nanosecond. It can be even lower. The only reason we did not use lower current pulses because these devices are not designed for this low pulse. Rather, these are so these devices work pretty well with 8 nanosecond pulse, and that will give a energy consumption per weight update is about only a few picojoule. And which is similar to the resistive random access memory I talked about. Now, the thing with the resistive random access memory is that the resistive random access memory are very skilled devices. Otherwise, they don't operate because the amount of current density you need is very high, or the amount of electric field you need is very high. So these resistive random access memory are very skilled. So it's not a fair comparison to compare our large prototype devices with the resistive random access memory. So I give you a comparison of other scale devices. So it's fairly easy to fabricate scale devices of a magnetic tunnel junction 20 nanometer in diameter, easily fabricatable in the industry, and cobalt iron wire of 25 nanometer is also possible to fabricate, and the domain wall also possible to move within this narrow wire. And we calculate this more rather conservatively. So we take the pulse width, keep the pulse width as 8 nanosecond, and then gives us a weight update energy required for this is about only a few 10 of femtojoule. Now, just to give you a comparison that how they compare with the biological synapses we want to create, that for the biological synapses, it also need about few femtojoule to change a synaptic weight. Now, it's not yet close, but it's possible to design these devices more energy efficiently, use different kind of materials for efficient domain wall motion that is possible to get this kind of femtojoule energy. So moving on, I will talk about how we can use this analog device I have shown at the first part of my talk, and use that devices for designing a system. So these are the analog devices I showed in my talk at the beginning, that we have magnetic domain wall under a long reference layer to create this linear variation, and we engineer the spin orbit torque generating layer to create this nonlinear functionality. And using these devices, we want to generate a system. And to give you an overview of the system with the three cross-point area of this three-terminal magnetic tunnel junction. So the main operation is the weighted summation of this cross-point array. So the signal comes through this read line, and they goes through all the current. All the current is summation along this bit line, and they go through this thresholding function, and that gives you the output for one layer. Now, that's not the only operation we need to do in the circuit. We also have to set the weight of the synaptic devices. And for that, we need switches so that we can decide which terminal we want to activate at a time. So for that, we need transistor, and the transistor are very easily incorporatable with the magnetic tunnel junction. So, and they act as a switch. And also to separate this activation function, there need to be required to be switches before the activation function generator device, so that it can be separated when the weight is updated within this synaptic device. And for the weight update, the switches are shorted. So the current is, so there is a voltage in the right line, and that creates a short of the switch. The switch is turned on. You can assume, and that gives that by applying a current or voltage between this signal line and the bit line, the weight can be changes 1 row at a time. And after the changing the weight, to make sure that the weight is operating, it's again activating the read line and the bit line that can read so that we can read the resistance of this each synaptic devices and know that the synaptic devices are updated properly. So this is again the whole layer in a simple 2x2 system, and the great advantage of this design, or the synaptic and the thresholding function, is that the output of one layer can be feed through the input, as an input to the next layer, and there no need to be any other conversion which is required for other non-volatile memories. So by using a thresholding function generator, by using a magnetic tunnel junction, we can do all the calculation in the analog domain, which is not possible for other non-volatile devices. So this kind of direct connection from going through this analog activation function generator to the input is not possible, because they don't have this kind of activation function generator. So what they have to do, they have to convert the signal into a digital signal again, and then convert it back to the analog signal before feeding them. So this nonlinear activation function is done as a digital form. So the signal has to go to analog to digital, then digital to analog again, between one layer to the other layer. So that requires a lot of energy and also a lot of circuit overhead, which is not beneficial. And definitely we are not taking advantage of the other non-volatile memories fully because of this not unavailability of this thresholding device. Just to give you an advantage, show you the architecture, how this cross-point architecture of these magnetic devices would look like. So it's very simple. The input-output, whatever that comes in as an analog signal, they go through the voltage driver. And there is a lot of cross-point area of a magnetic tunnel junction, which does all the computation of matrix multiplication and also the conversion thresholding, and then goes to the sense amplifier to the output. So in simple design, it's the cross-point architecture in the middle is these 4 layers. So they are same and they can operate simultaneously. So it's possible to run multiple layers together, or if you want, or if you don't want, or if you have a large layer, you can divide into multiple cross-point areas and do this one layer calculation into different cross-point areas. And then afterwards, it goes to this conversion, and it has some other circuitry related to the conversion of the input and output voltages between them in the periphery. And it's just to give you a comparison that this architecture is similar to resistive RAM. The only difference is that for the resistive RAM architecture, cross-point architecture, which is utilized for memory, they don't require the thresholding function, or in other words, they don't have the thresholding function generated. Moving on, the key benefits of such kind of cross-point architecture with this multiple resistance state of this magnetic tunnel junction is that it overcomes the accuracy loss for the calculation, which can be coming from if you do only the digital calculation, not analog computation. There will be a loss of total 20% accuracy. So your classification of any image or classification of any data will not be accurate. And then it's there is we as a people who work on the magnetic tunnel junction, we know that there are some device-to-device variation, and it's fairly possible to have those variations in a circuit or in a chip. But this neural network can be possible to can be trained in a way so that we can overcome those process variation fairly easily. And again, as I say, there is a direct layer-to-layer flow. There is no conversion between the analog to digital or digital to analog signal, so that saves a lot of computation energy and also a lot of processing time within that energy. And it turns out that not the multiplication, rather those conversion takes the overall most energy from that, maybe more than 70 to 80% of this energy we need to operate those. And we have done some power calculation of the 2x2 array for just to compare with the CMOS devices, and they require about microwatt of power. And we calculate also with we compare our devices with other non-volatile memories, and we have done some calculation, and for that we assume that we need about microamps of current, and that's still even about 5 times better than other analog devices. And for the other analog devices design, we have taken the data from this paper. And one of the other parameter we want to minimize is the computation time. So the latency of each layer is about 4 nanoseconds for using these devices, and assuming that we are using a 2x2 array of the synapses. The good thing is that we do the multiplication with a 1 cycle. So it's a matrix multiplication done with just 1 pulse, and which are not 1 pulse, like different pulses coming at the same time. So it doesn't matter how big your array is. It doesn't matter how big your array is. This 4 nanosecond will be constant for dependent and doesn't depend on the size of your array. So the final goal we want to see is that creating a device using this analog kind of synaptic device and analog thresholding device, and create and integrate them as in the back end of our CMOS processing, so that they can be integrated in a continuous fashion. So in the bottom there is all the transistors that require to be changing the synaptic weights or activating this thresholding function generator or not, or deactivating them. And these are all, so they are on the bottom layer, and in this back end of this, all the interconnects is these devices integrated. And it's fairly possible with the technology we have in the industry today. So it's a matter of time that we use this kind of chip for doing the actual classification for the images or any other data we want. To summarize my data or summarize my talk, today I have shown you a very different kind of thresholding devices, which is only possible with using the non-volatile magnetic random access memory, but not possible with the other non-volatile devices. I have shown you a very linear behavior of the synaptic devices with domain-wall magnetic tunnel junction, and also show you a different electrical read with the nonlinear thresholding devices using the magnetic tunnel junctions. And at the end, I have shown you a system by using this activation function generator and also synaptic devices, and how we can use them into the architecture to figure out any kind of classification task we want to use. Before ending my talk, I'd like to acknowledge the people who are involved in this work. So this work I have shown you today is done at my PhD. So my advisor, Mark Baldo, he was very instrumental in this study. And I'd like to thank also Caroline and Lucia, who guided me throughout this process of designing these devices, designing magnetic tunnel junction, and characterizing them. I'd like to thank my colleague, Sumit. He is instrumental in the circuit analysis part. And also to Astera, she is helpful in developing the magnetic tunnel junction and help me characterizing some of the tunnel junctions. At the end, I'd like to thank my postdoctoral advisor, Axel Hoffman. We had a numerous discussion about this kind of neural network and how the other synaptic, Spintronic devices are useful. So he broadened my understanding of those devices in a great manner. So thanks, Axel, for that. So with that, I'd like to also thank the audience, and I'm really sorry about all the technical glitches. I hope you still enjoy the talk. And if you have any questions, I would like to answer. Thank you.
There's the clapping, and everybody's typically stand your hands up to clap, but you put it back down immediately because now we need to ask the questions. So David, now you are, if you can open your microphone, maybe you can ask your question. Oh, sorry. More exciting news. So David, I think I allow you to unmute. Can you unmute yourself and ask your question? Or should I ask a question? Maybe your device is not on. It seems that he would like me to ask a question. So let me read the question. In your devices, the coercivity of free layers outside of pillars is much smaller than inside the pillars. Can you explain how domain wall can overcome this high energy barrier to enter inside the pillars? And how can't you avoid the random domain wall nucleation in the low coercivity area when you apply current to move the domain walls?
Yeah, that's a very good question. So let me go to the slide, I guess. Not this one.
Okay.
Yeah, okay. So the amount of coercivity is low, but it's not too low. So we can still, it's about roughly 20 worsted. So we do not see any random nucleation of the domain wall. At least from our experiments, we haven't seen that. So when we apply the current pulses, we observe there are, if you show you the results, so we observe that there are some stochasticity between moving these domain walls. I believe that's coming from the reason that they are pinned along these edges. So sometimes this stochasticity is really fairly large. So there are some still this stochasticity which not always move the domain wall with the same current, but it's as far as we see that we can still be able to move them with the amount of current we apply.
Okay, thank you. Eileen, if you unmute yourself, you can maybe ask your question. If you cannot, can read the question for you? Let me know. I think you now should be allowed to talk if you can. Okay, some speakers are like doing it from the. Okay, so it doesn't seem that Eileen is able to unmute herself. So let me read the question. In your multi-pillar devices where you nucleate domains in between pillars by a small magnetic field, you drive the domain walls by current. So this is similar in what David was asking. Have you tried the same experiment? So drive a current through the track without the nucleation step by field. Do you observe changes in resistance in this case if you've done this experiment?
So we haven't done this experiment that without applying field, without nucleation, trying to apply the domain, apply current. The main reason is that we reset our, we apply a very large bias field at the beginning so that we saturate the reference layers as well. And that way we confirm that everything is uniform and we start from there. I can tell you from my experience, not like exact experiment, that if we apply without nucleating the domain wall, if we apply the current, I do not believe we will observe any change in the resistance because there will nothing happen. It's already an uniform layer, so there should not be any change in the resistance of the magnetic tunnel junction or the area of magnetic tunnel junction.
So Justin in Korea, can you please go ahead and ask your question?
Okay. Can you comment on the future potential of Spintronic device toward the SNN elements such as STDP snaps or LIP neurons?
Yeah, so as I was telling you about the spiking neural network, there are other kinds of devices as explored by Dr. Mark Stiles or Dr. Julie Grolier. They're looking into the other type of spintronic devices where they can more mimic the biological synapses by creating the spiking and these are still devices of the magnetic tunnel junction. So I believe those are very good options, and they should be. And in fact, with the speed nano oscillator, it has been shown that these devices can actually do those classification tasks or separate these two different frequencies, and those are already experimental demonstration of that. So I believe that these spintronic devices are very promising.
Okay, great. Yang Xiao, go ahead and unmute yourself and ask your question, please.
Yes, thanks for the talk. And for neurons, usually we need to have the neuron can be activated, but after the signal has been sent out, it has to be returned to be deactivated. So in the MTJ with domain wall, I don't see how it can automatically deactivate itself, the neuron. So does this mean that you need to reset the neuron every time it has been used?
So when you're talking about deactivation, you means that their weight do not change, right?
Oh, no, I'm talking about the neuron. The neuron uses the sigmoid function. So you basically push the domain wall to certain positions so that it gives you corresponding, resistance. But if you don't do anything to it, the domain wall will stay there, right? Stay, for example, in the middle of
right. I got your question. So the thing is, I move on. So here you can see that the current goes through, and that defines that what the output voltage would be depending on how the domain wall moves under with this current. But you are right, when you want to go from one layer and then do the calculation, and then this layer should be resetted because now the domain wall is already on a different position, and without moving it back to the original position, it will only keep going further. It will not reset to its own position. So you have to do the reset position. I have to do the reset of the domain wall after one operation of the layer.
Oh, okay, thank you.
Excellent, so thank you. And then Shivali, go ahead and ask your question.
Hi, Saima. Dr. Siddiqui, that was a wonderful talk. My question is that I didn't get how would you train the neural network? Means I got the front propagation part, forward propagation, but how will you conduct back propagation in this model?
Right. So the thing is, you need some error calculation. So you have to calculate the error function at the end of the layer and then you can just drive all the signals in the backwards to create that. So that part is still we have to rely on the CMOS circuitry for doing the error calculation or differential error calculation, if you say. Then go backwards to change the synaptic device weight.
Okay, thank you so much.
You're welcome.
Okay, excellent. So I think with this, I don't see any more questions. And I would like to thank you. Oh, sorry, there's one more question. Let me get Shuzang. Yeah, I'll talk. So go ahead, Zuzang, please go ahead and ask your question. I think I muted you. Can you unmute yourself and ask your question, or should I ask?
Hi. Yeah, I think it's working. Do you hear me?
Yes.
Yeah.
Okay. Can you say a bit more about how you initially create the domain wall? Because after a process, possibly it's moved out of the magnet layer, then how?
Yeah, That's a very great question. So once we have shown that once the domain wall moves and they move and go to the other edge of this, and that's the end of the domain wall. So there is still some adjustment we believe for this design that we need to go through for having the operation, everything done electrically. Right now, for our prototype devices, what we do after the operation of one operation, we reset the devices by magnetic field still for our prototype devices. But I believe it's possible to adjust the parameters of the free layer or the reference layer to make the reference layer. So in this case, what we designed, having a synthetic antiferromagnetic layer, try to remove the any kind of stray field coming from the reference layer. We believe we still have some amount of reference field. That's why the domain walls are pinned at the edge. If it's and it's fairly possible. It's just a matter of going through more iteration to create this synthetic antiferromagnetic layer without any stray field, so that we can or other words, use some other kind of materials, say antiferromagnetic materials. It's possible to kind of remove these stray fields, and in that case, you don't have to worry about this nucleation of the domain wall in the way we are doing it.
Okay. All right.
Thank you.
Do you have? Okay, David asked another question. I see cannot. So I'll say for him because it's on the browser. Do you have issue to protect PMA of free layer from processing step? So is the PMA having an issue with when you do the processing step of the free layer?
So I'm not sure what kind of issue you are referring to, but what are the precaution we take is we want to the whole processing temperature lower. It's lower than what we need to set the synthetic antiferromagnetic layer, or lower than what we use for annealing this magnetic channel junction stack. So that's the main precaution we take.
Okay, excellent. So I think with this, if nobody asks one last little question, no, I think I would like to thank Saima once again for a wonderful talk. Everybody can raise their hands if you like now to agree with me, and also to be cool under pressure when this computer that now Axel has agreed to replace and give you a brand new one, we'll get it fixed up. So thanks you once again, I think, and with this,